this is mat175, lesson 3, section 2.4, and we're going to look at the library of functions and also piecewise defined functions. Okay, first we'll look at the library of functions where we have f of x equal to b. In other words, this would be the same thing as if we were to say y equal to, let's say, 5. Well, if you were to work through a table of values, if you had y equals 5, then 5 would be under the y column for a table of values of x and y. So y under the y would be 5, 5, 5, and you can have x any value for x. So if you had 0, 5, 1, 5, 2, 5, you would have a horizontal line. So anytime you have f of x equal to some number, it's going to be a horizontal line that's going to go through the y-axis at whatever that number is, whether it's 5 or b or whatever. Here, this f of x equal to x. Now this is a parent graph where the slope is 1, the rise is 1, the run is 1. Y-intercept is at 0, so it goes through the origin, and it's always up 1 over 1, up 1 over 1. And so we get this linear equation. Now here we have a square root function, and these are known as parent graphs, where we have f of x equal to x squared. So if we were to put 1 in here for x, you'd have 1, x is 1, put 1 squared, you get y is 1. And here if you had x is negative 1, well, negative 1 squared, negative 1 times negative 1 is positive 1. And so you get this parabola looking graph. Here you had if x is 2, well, 2 squared is 4, so that'd be 2, 4. If x were negative 2, that'd be negative 2 squared, you get negative 2, 4 there. And so this is a parent graph for the parabola that goes where the vertex is at the origin. Next we have a cube. And so here it kind of looks like a sideways S in a ways. Where here when x is 1, y is 1, well 1 cubed is 1, well if x is 2, well 2 cubed would be 8, so this would be 2, 8. And then 3 and 27 and so on. And then here this would be x is negative 1, y is, well, negative 1 cubed is negative 1, and so on. Negative 2, negative 8, and so on. So this is the parent graph for f of x equal to x cubed. Square root, parent graph starts off at 0, cannot have negative values inside here because that's imaginary. We only need, this graph's real numbers. So if you put 1, x is 1 in here, well the square root of 1 is 1. And so if you were to put in 4, right, it helps to use just even numbers that you can get an even square root, like 4. Well, square root of 4 is 2. And then the next one, 9, square root of 9 is 3, and so on. Well, if you put a negative 1 in here, it can't do that. That's imaginary. So, but 0 is okay, right? Square root of 0 is 0. So you're going to have a definitive point at 0, and it's going to go up and to the right. Here we have a cube root. And here, notice there are positive and negative x values. Well, let's examine the positive side first. First, 0, square root of 0, cube root of 0 rather, so that's still going to be 0. Cube root of 1, well, 1 times 1 times 1 is still 1, so cube root of 1 is 1. And now if we took 2 times 2 is 4 times 2 is 8, so if we had x is 8, then we would have cube root of 8 is 2. Well, 2 times 2 is 4 times 2 is 8, so the cube root of 8 is 2. And so on. Go on from there. Cube root of 27 is going to be 3. Well, you can have a negative for an odd root, because negative 1 times negative 1 times negative 1 is still negative 1. So that's okay. we can have a negative 1 out. We just can't have that for an even root. So negative 8, the cube root of a negative 8, that's going to be still negative 2. Okay, and so on. And so you get this kind of sideways looking S kind of graph where you get, here's your top half for your square, like you would for a square root, but then you get that S looking shape going in the negative direction as well. And so that's the parent graph for a cubed root. Here we have a reciprocal function where, guess what? What happens if you have 0 in the denominator? You get undefined. So right here, this is at 0, this function is undefined. And then we have what we call a horizontal asymptote going across this way. So when x is 1, we put 1 over 1 here, we get 1 still. But if x were 2, we put 2 in here, we get 1 half. X were 3, we get 1/3. X is 4, we get 1/4, and so on. And so this gets closer and closer and closer to 0, but it never does get to 0. Same thing with the negative direction. So we look at where these two asymptotes crisscross at, and that's the center of our reciprocal function. Absolute value, well, when we know that with an absolute value, even negative numbers for x, we still get a positive out, and that's why if we put negative 1 in here for x, we're going to get, because of the absolute value, we're going to get a positive 1 out. Negative 2 is going to be positive because of the absolute value, and we get a positive 2 out. And so that's why you get this V looking shape for the absolute values. Again, here we have a vertex at 0, 0. So this is the parent graph for absolute value functions. And then we have our integer functions. Now the graph in calculator may make it look like step stairs, but in reality, they're basically, what we have here is that there's 1 here. You can't see it because the intercept is in the way. You know, the x-axis is in the way. But it is closed at 0, and then it goes to 1, and that's open, and then it kind of hops up here at 1. So there's a gap in here. And then this is closed at 1, and it continues on, and then it's open there, and then it jumps again. And then this closed here, and it continues on, and you're going to constantly get these integers, where it's not going to change until it gets to the next integer. And you get, it looks like stairs in a way, step stairs in a way. Okay, so that's our parent graph for an integer function. Okay, graphing a piecewise defined function. Basically, we want to write, there's some steps here I wrote down to help you graph a piecewise defined function. First, we want to rewrite each part of the graph as a separate function. And then we want to draw a vertical line where x is where your limits are at, or where your restrictions are. X is greater than some number, or less than or equal to some number on the graph, on the coordinate plane. And we want to pay close attention to where the graph ends, whether is it open or closed at the ends, and where it stops and where it starts. Those are important because people tend to make a mistake on that part. Next, we want to draw each part of the graph from left to right. Use the table of values for each part. Indicate open or closed ends depending on the inequality sign for each end. And so where one ends, the next one begins, and where one ends there, the next one continues on from there. So there should be no gaps for the x's. There may be gaps for the y's, but there should be no gaps for the x's. Determine the y value at x equal to that number for each graph. Okay, so here we have a piecewise defined function, and so the first graph is negative x plus 1, where x is greater than or equal to negative 1 but less than 1. And then the other one is f of x equal to 2, where x equals to 1. Now that's just going to be a single point there. And x squared, f of x equal to x squared, where x is greater than 1. And so we want to find where f of 0 is, f of 1, and f of 2. Well, f of 0. Okay, you have to look to the right here to see which graph does this fall into. Well, 0 is in between negative 1 and positive 1, so we would use this first graph. So we would substitute 0 in here for negative x, and we would get 1 out. Okay, and that's what this is. We used the first graph because the 0 fell within this restriction here. Now f of 1, that falls in with the x equals 1 restriction, and so your answer is f of x equals to 2. There's no variable there, so your answer is always going to be 2 for that x equals 1. We're going to use the graph to find the next is find f of 2. Well, 2 is greater than 1. And so x, this would be 2 squared. The 2 would fall into this graph here. And so 2 squared would be equal to 4. And so the domain of f is negative 1. The domain of f is negative 1 to infinity. Because if here's our graph, we have negative 1, so we have x at negative 1, and we get graphs here continuing here. Now this dot here counts at 1, and then even though it jumps, we still get x is continuous, and so that's why we have the domain of negative 1 to infinity for x. The range is going to be all the y values, and so since y is 0, it's going to be open at 0 for our range, and even though there's a hole here, this point is covering, these values here cover your y value from 0 to 1. This point covers your value at 1, and then these points cover the rest of it, so this will be open at 0 to infinity. Okay, next, in the summer of 2009, Duke Energy supplied electricity to residencies of Ohio for a monthly customer charge of $4.50 plus 4.2345 cents per kilowatt hour for the first 1,000 kilowatt hours supplied in the month, and 5.3622 cents per kilowatt hour for all usage over 1,000 kilowatt hours for the month. Well, 300 falls in between 0 and 1,000. So that would be here on the graph. Here's 300, and so we would use the first equation because 300 falls in between 0 and 1,000. And so we would get 17.20 kilowatt hours out. And let's try that. So we would put in here 0.04234 times 300, and then plus 4.5, and we get 17.2035. And so on the graph, they have 17.20. Alright, so that's pretty close to what we had. Alright, let's try B. What is the charge for using 1,500 kilowatt hours in a month? Alright, Alright, so you try to figure out which one of the two equations we're going to use. Pause the video for a minute and try it out, and we'll see how you did. Okay, 1500. Is that between 0 and 1000? No. 1500 is greater than 1000, so we would use the second equation. So in that case, we would use 0.05362 times 1500 and minus 6.777. So we want to try what is the charge for using 1500 kilowatt hours in a month. Okay, pause the tape and try to figure out which equation you use, and then try that. Alright, let's see how you did. We got 0.053622 times 1500 minus 6.77, and we get 73.663. So here we go, we have 1500 and that's 73.66. Okay, that's pretty close to what we had, rounded that off. And so that's part B. Okay, if C is the monthly charge for X kilowatt hours, develop a monthly relating to the monthly charge of kilowatt hours used. Okay, oops, back up. And express C as a function of f of x. Okay, so and so that would be this here. Alright, and so that is all there is to lesson 3. We will get more into working with piecewise defined functions in class. Thank you.